Greetings everyone. I've got a couple more examples today. We're going to be covering one from slides 15 through 17 of the 114 Momentum 02 slides. That one you need to watch a video first. So the link is in the description. Watch that video and you'll get what we're talking about. Then we're going to switch up that example and change around some of the conditions of it and see how that changes the outcome of what happens in that example. I hope everyone has watched the video, and I hope that nobody has any ideas of trying that at home. Please do not try that at home. That's a very bad idea. There's always a possibility that if you do something like that, the bullet could ricochet off and hit you. So definitely don't do anything like that. Well, let's draw out that situation. We had a bullet coming in towards a block of wood. That block of wood was on some sort of apparatus that would let it swing, and so when the bullet embedded in the block of wood swung up by some amount, and the height of that block of wood changed. If we specifically look at maybe a center of mass, we haven't really talked much about center of masses this semester, but every object is going to have its center, and so if we look at the change in height right there, maybe we can figure out something interesting with that. So the prompt for this example: some dude fires a bullet, mass 0.01 kilograms, that's 10 grams. Velocity 450 meters per second. 450 meters per second. Into a pendulum made of a block of wood, mass 2 kilograms. This has a mass 2 kilograms. Of course, at the beginning, the block had no velocity. The block stops the bullet, which is then embedded in the block. They swing up a certain distance. How far? We're looking for that change in height that the block with the bullet lodged in it swing up. Well, what kind of problem is this? This is one example of a multi-part problem. It doesn't necessarily show that there's going to be multiple concepts used in this problem, but it's very clearly starting off as a momentum problem. You're having two things collide. One thing is getting embedded in another thing. That strongly presupposes that it is a conservation of momentum problem. But then we have to do something else. Conservation of momentum is not going to get us a height. We have to think about what would give us a height. So I'm going to let you pause the video for a little bit and try to think of what other principle we could attach with momentum and figure out the maximum height that this is going to go. We'll start with momentum and we'll conclude with something else. So pause the video and think about that for a moment. All right. What I think we should do is start with delta P is equal to 0 and treat it like any other kind of collision. And then, once we have the final velocity of the block and the bullet put together, then we can either use kinematics or, more likely, conservation of energy to determine the final height of the block and the bullet together. So we're going to start with delta P is equal to 0, and then in part 2, we're going to have delta E is equal to 0. Now often when you have a delta P is equal to 0 and a delta E is equal to 0, that means that we are doing an elastic collision, but this very clearly is not an elastic collision. This is a perfectly inelastic collision because the bullet gets lodged in the block. Review those slides about the difference between elastic, inelastic, and perfectly inelastic if you need to. So what are we doing? We're going to use this to find some final velocity. And we're going to plug that final velocity in there and use this to find the final height. Here, we're going to have a kinetic energy and eventually a potential energy. Let's talk about where to define initial and final points of this problem. The initial point will be the moment before the bullet enters the block of wood. The final point of the momentum part will be the moment that the bullet has embedded itself in the block of wood, and together they're just beginning to swing up. Then we're going to take that final velocity and use that as the initial point of a delta E is equal to 0 equation, and take the final point to be the moment that it reaches its maximum height. So this is a multi-step, multi-type of problem. We're using multiple different things that we've learned in physics to solve this problem. So let's begin. Delta P is equal to 0. P initial is equal to P final. Momentum initial bullet plus momentum initial block of wood is equal to momentum final bullet plus momentum final block of wood. So initial momentum is just the bullet in the block of wood, and the final momentum is again both of them. But initially the velocity of the block of wood is 0. Therefore, its initial momentum must be 0. Okay, we've got mass bullet, velocity initial bullet is equal to mass bullet, velocity final bullet, plus mass wood. Oh, sorry. That should be a W there for momentum final block of wood, times velocity final wood down here. We know that the final velocity of the bullet and the wood should be the same because the bullet gets embedded in the block of wood, and so they're going to travel together. We can say mass of the bullet, velocity initial bullet, is equal to, we'll factor that out, and say that the velocity final is equal to the mass, times the mass of the bullet plus the mass of the wood. So I've just set these two to be the same thing and factored it out. We can then plug in numbers. 0.01 times 450 is equal to unknown final velocity times these two put together. Well, that's going to be 2 kilograms plus 0.01 kilograms, 2.01 kilograms. It's not a bad idea to get out our calculators at this point. Can we solve for V final? Well, it's going to be just 0.01 times 450 divided by 2.01, and we find that the final velocity of the block and bullet together is going to be 2.24 meters per second. Well, that's nice, but that doesn't get us the change in height of the block. So what can we do? We can use our delta E is equal to 0. So delta E, technically it's equal to work, but is there any forces coming in from the outside after the bullet has lodged itself in the block of wood? No. So that 0, energy initial is equal to energy final. What kinds of energy are we looking at? Well, there's definitely the possibility of kinetic and potential, gravitational potential. I don't really see any springs in here. So kinetic energy initial plus gravitational potential initial is equal to kinetic energy final plus gravitational potential final. Let's determine where to set h equal to 0. I'm going to say we should set h equal to 0 to be there at the center of mass of the block. So that's going to say that this is 0. Kinetic energy initial. I want you to think about what the initial kinetic energy is going to be. Is it going to be 0? Is it going to be something else? I'll give you a moment to think about that. Okay, the kinetic energy initial should be whatever energy we get from this. It should not be zero. We're having a different set of initial and final points now. In fact, the initial point that we have here is just before the bullet hits the block, and the final point is just after it has embedded itself in the block of wood, and it's just barely beginning to swing up because it has that velocity right there. That final velocity for this problem is going to be the initial velocity for this problem. We need to use this 2.24 meters per second as for the initial kinetic energy. 1/2 mass times velocity initial squared. Now, what is the mass going to be? I'll give you a moment to think about that. The mass is going to be the mass of the bullet and the mass of the block of wood together. Velocity initial will be that. And that is equal to, well, we need to define the final point. The final point is when it's going to have swung up as much as it possibly can. What is the kinetic energy when it is swung up as much as it possibly can? Give you a moment to think. All right, I hope that you said the kinetic energy final should be 0. That means that the potential energy final is still going to be mgh. Turns out we can just cancel out those masses. Now we can say 1/2 times 2.24 squared is equal to 9.8 times our final height. And we can solve for that. 1/2 times 2.24, I'll just use this, squared, divided by 9.8, is going to be our final height, 0.256 meters. Height, 0.256 meters. I want to do this problem again, but with one change to it. In the first example, we had the bullet get lodged in the block of wood, and so they had the same final velocity. I'm going to change that and ask what is going to happen if the bullet actually does ricochet off of the block of wood. I want you to pause for a little bit and think, what is going to change here if the bullet bounces off the block of wood? Is the block of wood going to be going faster or slower than it did in the first example? Is the height going to be greater or less than in the first example? First example being where it embedded itself in the block of wood. Give yourself a minute to think about that. What is going to change about the final outcome of this problem? Okay, let's try it out. We're going to have the bullet come in, hit the block of wood. Bullet will still have a mass of 0.01 kilograms and an initial velocity of 450 meters per second. It's going to hit the block of wood, bounce off the block of wood. The block of wood will still swing up, as you can probably imagine. If something hits something else, then it's still going to swing up, even if it doesn't connect together. I'm going to draw our center of masses right there. So we're looking for that change in height. And to do this, we have to figure out what speed the bullet bounces off the block of wood. Now, there's no way of doing this, of calculating that, without actually doing an experiment. So we have to just make up a number. Presumably, the bullet will bounce off the block of wood at a speed lower than 450 meters per second. So I'm just going to make up that it bounces off at 250 meters per second. That's going to be my made-up number for this, just so we can see what happens if there is a ricochet like this. Now, the rest of this problem is going to operate just the same as the example problem. Momentum initial is equal to momentum final. Momentum initial bullet plus momentum initial wood, oh wait, that's 0, is equal to momentum final bullet plus momentum final wood. Mass bullet velocity initial bullet is equal to mass bullet velocity final bullet plus mass wood velocity final wood. Let's plug in numbers. Mass of the bullet, 0.01. Velocity initial of the bullet, 450 meters per second. Mass of the bullet, 0.01. Velocity final of the bullet. Okay, what should I plug in here? I'm going to give you time to pause and determine what I should plug in for the velocity final of the bullet. If you said negative 250 meters per second, be happy. The number one mistake that people will make on a question like this is they'll still have the bullet going this way after it hits the block of wood. And that's not how a bullet ricochets, is it? If it ricochets, it's going to hit the block of wood and bounce off. And so if it's bouncing off, then we need to give it a negative velocity. Be very, very careful about that right there. Okay, we can add to that the mass of the wood, 2 kilograms times the velocity final of the wood, and then we can solve. So on the left-hand side, we've got 0.01 times 450, and if we add this to both sides, then we get rid of that, times 250, and then divide that by 2, and we get velocity final wood is equal to 3.5 meters per second. We can then use this to find the final height of the block of wood. Delta E is equal to W, but W is equal to 0. And energy initial is equal to energy final. Kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. Is there kinetic energy initially? Well, the initial point of this problem is going to be the final point of this problem, the final point of this part of the problem. We can plug in the 3.5 meters per second that the block is moving after the bullet ricochets off. We can plug that in for the velocity we'll use here, and then use that. The gravitational potential initial is still going to be 0 if we define h equals 0 to be the original center of mass. And the kinetic energy final will again be 0. 1/2 mass of just the wood, in this case, times velocity initial squared for the wood, which we're going to take right from here. That's equal to mgh, and that's the mass of the wood, so that cancels out. We get 1/2 times 3.5 squared is equal to 9.8 times h. And we can calculate that. 1/2 times 3.5 squared divided by 9.8 is going to be h is 0.625 meters. Let's look back at our previous answers. This set of answers was for when the bullet embedded itself in the block of wood, whereas these answers were when the bullet bounced off of the block of wood. Is this surprising to you? If the bullet embeds itself in the block of wood, it is going slower and it doesn't go quite as high up. Whereas if the bullet bounces off the block of wood, it actually goes faster and it goes higher up. That's a consequence of the conservation of momentum. I want you to think about that concept right there and make sure that you understand why this is from a mathematical perspective and from a perspective of real life. Think about, for example, you standing up on a ledge somewhere and your friend throws a basketball at you. You've got two options. You can either try to catch the basketball, or you can let it bounce off of you. If you're trying to not fall off the ledge, would you rather catch the basketball or let it bounce off of you? It looks like if it bounces off, you're going to be going faster than if you just catch the basketball. Keep that in mind and think about that from a real life perspective.